All right, so today, guys, what we're talking about is the square root function. So we're introducing a brand new idea because last time we talked about rationals and rational functions. So now what we want to look at is maybe different types of exponents. So, and we'll talk more about that as it kind of goes. So the family function name that we're going to be talking about today is the square root function. Okay. Now the parent equation for this one, right, is kind of just as you would guess, is if I have f of x is equal to the square root of x. Okay. Now there's it's going to be a little bit different with this one, just because it's going to look very similar in some ways, but at the same time also not. So I'm going to, in the verbal description, I'm going to go ahead and I'm going to do my little table that I normally do, but you guys please feel free to write down any verbal descriptions that you start to see. Okay, so anytime we have a brand new graph, what we're going to do is we're going to create just a table. Okay, and we're going to look at different values kind of everywhere. So the first one that we always start with is 0. So if I take the square root of 0, right, that's always obviously going to be 0. So very similar to how we've started every other Cosmic Catalog, we're going to start off at 0, 0. Okay? So this gives us 0.00. Now we want to look at, okay, let's go to the right a little bit. So if I look at x, if x is equal to 1, right, that means that f of x is equal to the square root of 1, which is just simply 1. So my second point is just 0, 1. Okay. So again, starting off very similar to what we did before. Now, normally at this point I would choose 2, right, but the problem with choosing 2 is if I do 2, that means f of x is equal to square root of 2, which is an irrational number, which I can't really plot on here. So instead what I'm going to do is I'm going to choose a value, right, that I know has a perfect square root. Let's use 4. Okay? So if I do the square root of 4, right, that's going to be equal to 2. So my next point is going to be, oh, I put zeros for those. I'm sorry, guys. My next point is going to be 4. I cannot write right now. It's going to be 4, comma 2. Okay. So if I'm going to go over here to 4, I'm going to go up 1, 2. And we're going to see that this is kind of looking a little bit weird because it looks like it's going to just hug really close to the x-axis. So now what we're going to do is we're going to look at the left side and see what happens. Sorry. The left side, if I look at negative 1, what's the square root of negative 1? Who remembers? All right, it's
Is it the is it 1 with the I, the imaginary number?
yeah, it's the imaginary number, right? So this actually does not exist, right? As far, because again, we're graphing this on the real plane. So since it does not exist, and if you think about it, if I move any value of x that's to the left essentially, or in the negatives, right, this thing's not going to really happen, right? So nothing to the left is really going to work here. So I can't choose anything less, so I'm just going to keep choosing positive numbers, which I know have, you know, perfect square roots. So after 4 comes 9, because I know the square root of 9 is equal to 3. Okay? So my next point would be 9, comma 3. So I'm going to go over here to 9, I'm going to go up 1, 2, 3. And hopefully by now you're kind of starting to see, hey, these x's and y's, they actually look very familiar. We've had a kind of a function that looked like this before. Well, when I go ahead and I graph this guy and I start connecting the dots, right, it's definitely a little bit more curved. And what you're going to hopefully start to see is this guy looks very similar to a parabola. It just kind of went from here and whoop, and just kind of fell to its side and lost half of it. Okay? Now, the reason that we don't include the plus or minus in here, right, is because this function, right, it wouldn't be a function if we had the plus or minus. Okay? And that kind of just goes into where our defining characteristics come into play. Okay? So if I'm graphing this thing, right, again, we notice here that this point, we're going to call this the vertex, right? even though it's not quite really a vertex again. It acts like a vertex insofar as this is kind of where we start, but it doesn't act like a vertex in really any other fashion than that. It's just kind of, this is like our initial point, our starting point. So if we do our defining characteristics, we actually notice that this is one of the first ones that we have a restricted domain. Okay? My domain this time is not all real numbers. Where is it? What's my domain? Where do I start? Tell me. Anybody? All right, so if I kind of imagine taking this ruler here, okay, and if I'm looking at my function kind of going, all right, I'm going left to right, right, where does this thing start? It starts here at 0, okay? It starts at 0, and then just kind of moves on and on and on and on. So no matter how big of an x value I choose, right, I'm going to get some sort of output out of this thing, okay? So my domain is actually going to be from 0 to positive infinity. Now the reason I can't choose any value that's less than 0 is because any value that's less than 0 will give me an imaginary number, and we're dealing with the in the real plane, okay? Now the range of this guy is also going to be restricted, okay? So again, now I'm going to take this ruler, I'm going to turn it sideways. I'm going to start from bottom to top, okay? So I'm going to start here at negative infinity, I'm going to go up, and I can see that my graph, I don't really have my graph until I get up to 0, right? And then moving up. Okay, for whatever reason, my ruler's not being very friendly right now. Okay, so it just starts at 0 and then it goes up. But you can see that, like, I mean, if you think about it, think about the biggest value of x you can have, and it's as far as positive, and it's still going to have a square root. So my range is also going to be from 0 to positive infinity. Okay. Now this function, right, as you can see, it starts over here at 0, 0, and again, as we're moving from left to right, we notice that the slopes at each individual point look like this graph is positive. It keeps going up and up and up. My slopes kind of, I mean, even though it goes up and it looks like it kind of stalls out a little bit, right, my graph is still slowly increasing, okay? So this graph is constantly increasing, which means that, but because it's even though it's always increasing, we don't use the fact that it's all real numbers because it's because there's nothing to the left. So it's only increasing on the domain. In this case, it's also never decreasing. As far as horizontal asymptotes and vertical asymptotes are concerned, we don't have any, right? Because if we look at this graph, right, there's no value other than this kind of weird to the left thing. Right? It's not really an asymptote. It's just not really defined. Okay, so nothing. It doesn't look like this guy gets really close to one number and then never touches it. Right? It's just there's nothing. So there's none. No asymptotes. We'll get to x and y intercepts in a little bit. Minimum value, actually we can do the x and y intercepts for this one, because if I look at this function, right, we can see that this point right here, the center point, right, that's both the x and y intercepts. And if we keep picking values that are greater for x, we notice that it's never going to just come back down and touch the x-axis again. So my x-intercept and my y-intercept are the same thing. X is equal to 0, y is equal to 0. Okay? Or we can say 0, 0, 0, 0. Okay. Maximum value, minimum value. This thing's going to go up and up infinitely, so we're going to have a maximum value. But its minimum value, I mean, again, it stops right here at 0. So realistically, it does have a minimum value at 0, 0, or y is equal to 0. Actually, I'm gonna write that the other way around. Is it 1 to 1? Well, we know it's a function because it passes the vertical line test, and we know it's 1 to 1 because it passes the horizontal line test. As I move up, right, it only touches the ruler in exactly one place, minus my horrible sketchings. Okay, so it is also 1 to 1. Slope, nonlinear. Vertex at 0, 0. Ooh, that looks ugly. My vertex is again at 0, 0. All right, and my axis of symmetry, I have none. Now that's going to seem a little bit weird, axis of symmetry, and we'll talk about that more when we look at this function in a slightly different way. Right? But this is essentially our square root function. Okay. Now we're going to look at it. Okay, what happens if we add some elements to it? So just like normal, we're going to talk about the transformations. Now instead of doing like actual explaining the blah 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 the transformations like we normally do, I'm going to show you the Desmos that we have, right, and kind of talks about it. Okay, so here we have our Desmos graph, and the black is our parent function, okay, which is just the square root of x. Now, just like the other general rules of transformations, if we look at g of x, right underneath, we can see that it's equal to a times the square root of x minus h plus k, right? And just like all of the other functions that we have talked about, right, these a, h, and k all do the exact same thing that they did before, okay? So if I look at a, and if I increase a, so a is always initially 1, h's and k are always initially 0, okay? So if I'm looking at this function right now, if I'm graphing it, I can see that it's 1 square root of x minus 0 plus 0, okay? And that's where my parent function essentially lies. Now if I start to change a, you can see, right, I start to increase a, so the bigger a gets as far as greater than 1, right, the more this thing vertically stretches, okay? But now if I go between 0 and 1, right, we can see that this graph starts to shrink. And so again, it's my y, it has control over my y values. My y values are shrinking. It's vertically stretching if it's greater than 1, and it's compressing between 0 and 1, okay? And then once I get to 0, obviously, you know, I just get a flat line. But, right, once I go below 0 and we go negative a values, right, this graph starts to flip. Isn't that interesting what it looks like if I just directly flip it? Weird, okay? And then so on and so forth. And so again, if it's greater than 1, right? If a is greater than 1, it'll stretch, but between 0 and 1, it compress, and then that negative, all it does is flip it across the x-axis. Okay, go back to 1 here, and we can see that. Stop. Right, you can see that h, right? So if I'm graphing this now, it's still 1 times the square root of x minus 0 plus k, or plus 0. Now if I increase h, again, I'm going to move to the right h number of units. You can see where our graph, or where our initial point here for our parent function, if it'll let me touch it, was at 0, 0, and now it's over here at 3.050. Yeah, there we go. At 0, 3, 0, 0, 0. And so h is going to, again, just shift that vertex like to the left or right, however many units, okay? And then k, just like you'd imagine, is going to shift it up or down that many units, okay? So if we kind of look at some examples here, so this is my parent function, y equals square root of x, right? Now if I just take a and I write it as, if I look at the equation y equals 2 square root of x, right? What do you think is going to happen? Are we going to have a vertical stretch or a vertical compression? I want you guys to give me a thumbs up or a thumbs down here. If it's a vertical stretch, give me a thumbs up. If it's a vertical compression, give me a thumbs down. What do you think y equals 2 square root of x is going to do? Vertical stretch or vertical compression? All right, we're going to have a vertical stretch by a factor of 2. So what I can imagine is I'm going to take all of my y values, right, and they're just going to be multiplied by 2 essentially. So if I look over here at 1, 1, sorry, if I look at this, if I look at this graph, oh my goodness. If I look at this graph and I hold it to this point, if it'll let me do it, right, my initial point was 1, 1. 1, 1. It'll let me hold there. You guys can see that it was 1, 1. Now, if I multiply all those values by 2, my initial point should now, or that point that was at 1, 1, should just go up to 1, 2. Same thing with 4, 2. Now went to 4, 4. 9, 3 went to 9, 6. So all it does is multiply my y values, okay, by that factor. If I do it by 0.5, it's going to shrink it, right, by half. So over here I was at, again, this is my parent function. This black one's my parent function, right? I'm at 1, 1. And then if I look at the purple one, it should be 1 and half of whatever that y value is, or 1 and 0.5, okay? And so on and so forth, okay? Again, the negative will reflect it, and then -4 will reflect and stretch it, okay? And that's the effect that A has on it. But notice here that A did not have any effect on where this thing started at all. In every single case, it starts at 0, 0. Now, and that's just because A just is vertical stretch and vertical compression. That's the only thing it has an effect on. Now, if I look at H, okay, again, here's my parent function, right, and I can go to the right 2 units. I go to the right 0.75 units. I go to the left 7 units. I go to the left 5 units. Okay? And that's kind of the effect that H has on it. And again, I'm just kind of breezing through this because we've seen a lot of this type of action before, especially with H and K. So this shouldn't be much of a surprise. And notice here that K is outside of the square roots. That's the most important part. H is inside the square roots. K is outside the square roots. So it's just like what we've done before. H is inside the parentheses. K is outside the parentheses. It's that same idea, except for the parentheses now are just our square roots. Okay, and we can see that if I have x minus 4, I'm just going to shift down. If I go plus 6, I'm going to shift up. And then this -3, right, plus square root of x, imagine you can actually rewrite this, right, as square root of x minus 3. So this thing is actually going to go down 3 units. Okay? And that's kind of the effect. So please remember, right, that even though it may look funky like this, and just like the last one and this one did, right, even though they kind of look funky, if you just kind of remember where you're, like, what it's supposed to look like, rearrange it to look like that, it'll be a little bit more visible, okay? And then if we look at all of them together, like ones that have all of them, right, we can see that in this case, all we did was stretch. We moved to the left 1 unit and then down 2 units. And then for this one, we went to the right 4 units, right, because H is 4. Then we went up 4 units, but this negative, it belongs to my A, so it actually reflected. Because I could rewrite this as negative square root of x minus 4 plus 4. Okay? Again, I'll let, this link is in the module, so if you want to look at it, you can feel free. Okay? Last thing that we're going to talk about. Okay? Is now we're going to kind of graph these guys. Okay? And then we're going to do our defining characteristics. And then once we get done with this, I'll set you guys free to work on your assignment today. Okay? All right. So if I'm going to graph g of x, so this very first one, okay? So again, the parent function is the square root of x. And if you ever feel like, you know what, I want to have the square or the parent function on there, please feel free, right? So for example, I could go ahead and I could plot the parent function, which is 0, 0, 1, 1, and then it was 4, 2, then it was 9, 3. And I'll just do a little dotted line or something like that to kind of represent. So this is my parent function. So this right here is y equals the square root of x, or f of x equals the square root of x. So now when I'm transforming this thing, it might look a little bit easier of how I'm supposed to graph this. So again, I want to look at what my values are. Okay? In this one we have, I'm going to use green for this one. We have a is equal to 2, h is equal to positive 1, and k is equal to 0. Okay? So I'm not going to go up or down at all. What this tells me is I'm going to vertical stretch by 2, and then this one's going to tell me, I'm sorry, I wrote that horribly. Let me write this a little bit better for you guys, sorry. So, my a is equal to 2. Oh, wow, I don't know why it's doing that. Which tells me vertical stretch by 2. I have h is equal to positive 1, which means shift right 1 unit. And then k is equal to 0, which means no up or down shift. Okay? So I'm going to take the same values, all right, and I'm going to use a couple different colors here. Again, this is just kind of one of the ways we can do it. First thing I'm going to do is I'm going to shift it. Right? I'm going to shift it. I'm going to do h equals 1. So I'm going to take all these points that I have, and I'm just going to shift them to the right 1 unit. So at this point right here, I'm going to shift it to the right 1. This point right here, I'm going to shift it to the right 1. I'm going to do that with every single point. And so what I'm going to get is essentially the exact same graph, just shifted 1 unit. Okay? And now, once I've got that, now I'm going to take all those points, and I'm going to use green for this one because this will be our finished one, right? And I'm going to stretch them by a factor of 2. So I'm going to start here, but then all of my other values, or I'm going to multiply the y values by 2. So this one's 0, 0, so that's going to stay there. This one is I'm right here at 1, so I'm just going to double up how much I went. I went right 1, up 1. I'm going to go right 1, up 2 now. To get to this point, I went right 4, up 2. So instead, I'm going to go right 4, up 4. So I'm going to go up 1, 2 more. And then for this one, for this point right here, I went right 9, up 3. So instead, I'm going to go right 9, up 6. 3, 4, 5, 6. And so my finished graph should start here and look like this. Again, a rough sketch is okay. All right, but that's all the effect that all of these guys have on it. Now, again, I can go ahead and erase all that other stuff if I want to, right? But I'm just going to kind of write it as is. So this blue represented just simply y is equal to the square root of x minus 1. And then this green represented my finished one, which is y is equal to 2x minus 1. Okay? And that's how we can graph those. Defining characteristics now. Okay? So again, I'll use green still because that's the one that we're on. If we notice that our defining characteristics are domain, right? Everything shifted to the right 1 unit, so I can't ever actually choose 0 in here. So my domain is actually from positive 1 to positive infinity. And my range is going to be, but again, my range is again looking up and down. My range is from 0 to positive infinity. It's forever increasing, but it's only increasing on its domain, which is 1 to infinity. It's never decreasing. Again, we talk about square roots. They don't have any asymptotes. Our x-intercept in this case, we can see is over here at 0, 1. So it would be 0, 1, or y is equal, or sorry, x is equal to 1. No. Sorry, I said 0, 1. That's dumb, Mr. Kiefer. It's 1, 0. Is that 1, 0, or x is equal to 1? Our y-intercept, in this case, right, does it ever actually cross the y-axis? No. Okay? So we have to be careful. We will not always have an x and y intercept. because my graph is not defined everywhere, right? We may or may not have x and y intercepts, so you have to use the graph to kind of check. Y intercepts, we actually have none. Maximum value, this thing goes on and on up forever, so it has none. Minimum value is going to be wherever my vertex essentially is in this case. So it's at 1, 0, or y is equal to 0. 1 to 1, yes. Slope, non-linear. My vertex is same place my x-intercept was, same place my minimum value was, which was 1, 0, and there's no axis of symmetry. Okay. And so that's kind of how we can use it as far as that's concerned. I'm going to do the same thing on this one. Okay. So now I'm going to identify what my A, H, and K are. In this one we have A is -1. Sorry. I forgot I needed to find what that does. So A is -1. Which means that we have, only thing that we have no vertical stretch or compression. The only thing we have is a reflection. About the x-axis. Okay? My H is equal to -2. So we go left 2 units. And my K is, My K is equal to 3, so we're actually going to go up 3 units. Okay? So I'm again, I could, if I wanted to, I could go ahead and just plot the parent function, which again was here at 0, 0, 1, 1, 4, 2, 9, 3. And go ahead and plot that. I'm just teaching you guys this way this time in case it's a little bit easier for you as far as graphing is concerned. I know most of you guys are probably just using Desmos, right? But this is a nice little alternative. Okay, so this is my parent function, y equals the square root of x. I'm going to use blue for my shifting to the left 2. So I'm just take all these points. I'm going to shift them left 2 units. So I'm going to go 0, 0. I'm going to go 1, 2 to the left. I'm going to take this 1, 1. I'm going to go to 2 to the left. And so on and so forth. I'm going to do that with each one. So this is 4, 2, 1, 2. This is 9, 3, 1, 2. And this is kind of what my function looks like as far as that's concerned. So the only thing that I've done here with the blue, right, is I've shifted to the left 2. So what I've actually just graphed here for the blue is y is equal to square root of x plus 2. Now I'm going to take that and I'm move it up 3 units, except for this time I'm going to use yellow for K. I'm going to take all of these points that I just moved to the left and I'm going to move them up 3. So I'm going to take this point right here. I'm going to go 1, 2, 3. I'm going to take this point right here. I'm going to move it 1, 2, 3. I'm going to take this point right here. I'm going to go 1, 2, 3. I'm going to take, this point right here. I'm going to go up 1, 2, 3. Is that the right point? Hang on, that's not the right point, I don't think. So, it should be right here, sorry. Okay. And then I'm going to graph it. Okay, and so what I've just graphed right here is y is equal, so I've included the shift to the left, so square root of x plus 2, but then I've also gone up 3 plus 3. Now the last thing I need to do is I need to reflect this thing, and again I'm going to use green for that. And I'm just going to take all those points and I'm going to just imagine, as again, it's supposed to be reflected over the x-axis, but you need to be careful, okay? My x-axis, essentially where that kind of points has shifted, right, to I have something like this, like to essentially, this is where my new grid essentially is just moved to. So my reflection's not going to be necessarily over the x-axis. It's going to be flipping again kind of over itself. Okay? So I'm just going to basically mirror all of these points on the yellow, and I'm going to mirror them down. So 0, 0, and then I went right 1, up 1. Instead, I'm going to go right 1, down 1. Right 4, down 2. Right 9. Hold on, let's see. 9, down 3. Okay? And that's essentially where I'm going to graph this guy. And so my finished graph, I know I'm drawing horribly. Something like this. Okay? And so you're probably going, okay, that's a whole lot of mess in here. So what I'm now going to do is I'm actually going to erase all of the other stuff that isn't the green. And there you have your graph. Okay? I know, I hopefully you guys are still with me. Okay? And that's just kind of how I can do that. So again, my domain now, if I look over where it's kind of started, I'm over here at negative, let's see, negative 2, positive 1, 2, 3. So my domain is actually from left to right, starts at negative 2 and goes to positive infinity. My range, instead of going from bottom up, right, and starting at this vertex point and going up, it actually ends there. So my range is actually, in this case, going to be from negative infinity up to positive 3. Sorry, that needs to be a bracket. Okay? Is this function increasing anymore? No. When we do that reflection, it's now switched. And instead of having always increasing, it's actually always decreasing. So it's never increasing, but decreasing constantly, sorry, that's wrong, along the domain. Okay? No horizontal and vertical asymptotes. The x-intercept. Okay? And again, we'll teach a different way how to do it the next time. Like in before, but when we did cross, right? Remember we crossed right at. Hold on, it's gonna be, It's gonna be at, I believe it's, is it 5, 0 or is it 6, 0? I think it's at 5, right? 9, 3. No, it's 7, 0, right? Yeah, it's 7, 0. So when we plotted it, my x-intercept was actually at x is equal to 7 or 7, 0. Y-intercept, a little bit trickier. In order to do my y-intercept, remember we set x is equal to 0. So I'll do that right now. Intercept, set x is equal to 0. So I can just solve. So the reason that we're going to do that is because when we do this, so we have y is equal to, where's my graph? Negative x. Negative square root of 0 plus 2 plus 3. So my y-intercept is actually going to be negative square root of 2 plus 3. And that can't be simplified anymore. So that's just simply what our y-intercept is. So it's going to be y is equal to negative, negative square root of 2 plus 3. And again, you can use Desmos to evaluate that if you'd like and estimate it, but that's kind of all we have. Our maximum value, we do have a maximum this time because, I hate that it does that. We do have a maximum value this time, right, because this is the highest, this point right here is the highest point on my graph. So since that's the highest point, that point is at negative 2, positive 3. My maximum value is at y is equal to positive 3 or negative 2, comma 3. However we'd like to write it. No minimum value. It's 1 to 1. Non-linear slope. Our vertex, at least what we're calling it, is at negative 2, comma 3. And we have no axis of symmetry. Okay? All right, I'm going to go ahead and I'm going to stop the recording right there.